This is Dr. Carroll, and this video is about binary search trees. Binary search trees are great. They provide a simple structure to allow us to be able to find things much more efficiently. They just have a few rules about them, so let's cover that before we get into the exercises. There are 3 rules for each node of a binary search tree. The first one is each node, its value is going to be greater than all the values in the left subtree, T sub L. And also that its values are less than all of the values in the right subtree, or T sub R. And then finally, our recursive part here, that the subtrees T sub L and T sub R are themselves BSTs. And so with those simple rules, then we can get great gains in terms of finding nodes in the tree. So let's jump in and do some exercises. Let's start by building up a tree to make sure that we understand how to insert things into a binary search tree. So I've just chosen some strings here: BS, AVL, TT, TTF, RB, splay. You might recognize some of those. And we're going to use those as our search keys, our keys to build up a tree. So to start off with, we would insert BS. There we go. There's a tree with BS in it. Very simple. Now let's insert AVL. Now BS is the root. We're not going to undo that in a binary search tree. And we need to make sure all of those 3 properties were observed, so there's only one place that this can go, and that's going to be a left subchild of BS. And so then to insert AVL, we would have a tree that looks like this. BS is the root, AVL is the left subtree. All of those properties are, we haven't violated any of those, and there we go. You may want to pause it at each time we do a step in building this tree and make sure those properties all are honored. Now let's insert TTF. Let's see, TTF, there's only one place that we can insert it into this tree, and that would be a right child of BS, because it has to be greater than BS, and so we could put it there. Now TTF, there's only one place we can insert TTF, and that would be a right child of TT. All of the properties of a binary search tree are observed. Now we need to insert RB. So it has to be greater than BS, it has to be less than TT, so then we found the place for it, and so we could put it right here, RB, and there we go. We now have our tree. And then the last one is splay. We know it has to be greater than BS. We know that it has to be less than TT. And we know that it has to be greater than RB. So we can put it right here. There we go. This is our binary search tree with those strings added in. Let's now move on to talk about removal from a binary search tree. So given a binary search tree here with B as the root, A as the left subtree, and then B's right subtree has E, which has a left subtree of C, and C has a right subtree of D, going back to E has a right subtree of F, then let's talk about what it's going to look like after removing B and then after removing E. So let's start with removing B. So before we jump in, I thought let's look at some skeleton code for this. So if we're going to delete a node here, then it's going to have 3 parts. And to remove a node depends on one of 3 conditions. Is the node a leaf? Does the node have 1 child, or does the node have 2 children? And so let's go through each of these. If the node is a leaf, then remove it from the tree. Easy. We're done. That will preserve all of the attributes of the binary search tree. to remove it. But what if it has a child? If it has a child, then what we're going to do is basically replace it with the child, and then everything is preserved. All of those three properties are still preserved. Now, if it has two children, it gets a little more complicated. What we need to do is find the in-order successor, which is the leftmost node of that node's right subtree. That will be a leaf. Said differently, the in-order successor, the way you find it is you go to the right subtree and then you go to the left as much as you can until you hit a leaf, and that's the in-order successor. That is the node whose value is just barely larger than the current nodes. We're going to replace the current node's key with that one and then remove it. Really, we're replacing it in the tree with that one, as indicated by the key. So let's jump in and talk about removing B here. So to do that, let's see, B has two children. So then we're going to need to find its in-order successor. Let's see, go to the right subtree, which is E, and then go to the left until we can't. That's going to be C. And then we're going to need to replace B with C. Then we're going to have to find C's in-order successor because we said remove it, and then which is going to be D, and then replace C with D. So to go through those again, we're trying to remove B. We find B's in-order successor. We come down to the right subtree, and then we go down left as far as we can. So then we replace B with C, but now we need to remove C. So then we look and see, let's see, if node is C, then it has one child. So then we figure out which one it is. And so there's only one child, and so we replace C with D, and then we remove D. To remove D, we come up, D is a leaf, and so we just remove it. Remove D. And there we go. We have removed B. Okay, so now let's go through and talk about removing E. Let's see, E again has two subchildren. So we need to find the in-order successor of E, which is going to be F. And so we found it. And now we replace E with F, and then we remove E. Well, E is just a leaf, and so we remove it. And that's what the binary search tree would look like after removing E as well. Let's go through another exercise. I thought it'd be fun to insert the same strings into a binary search tree, but I've changed the order. Let's see if it makes a difference. We'll start with AVL. So pretty easy to insert into an empty binary search tree. It's the root. There we go. Now to insert BS, let's see, it would have to be a right subtree of AVL because BS is greater than AVL lexicographically. There we go. Now if we wanted to insert RB, let's see, there's only one place we could insert it. Has to be to the right of AVL, has to be the right of BS. There we go, inserted RB. If we want to insert splay, it has to go to the right of AVL. It has to go to the right of BS. It has to go to the right of RB. And so that's where it would go. Very strange tree. If we wanted to insert TT, it would have to be to the right of splay. And you guessed it, TTF. If we were going to insert it, there's only one place in this binary search tree that we could put it. It has to be the right subtree of TT. So is this a binary search tree? If you look at all three properties, they're all observed at all levels. It is a tree, looks more like a vine, but it is a binary search tree. This is important for our discussion about efficiency. Let's talk about average case for a binary search tree. So retrieval, if we're trying to find something The average case is the tree is going to be roughly balanced, and so we're looking at the height of the tree for its runtime. So on average, it's going to be log n, which is way better than a linear search. Log n is going to be so much faster. So to find somewhere, find something in a binary search tree on average is going to be log n. Insertion, we need to find where it would be and then insert it. So it's also log n because it's based on the height of the tree, which is going to be log of n. To remove something, we need to find it to be able to remove it. Now, we might find it and then need to find something else and find something else, but it's still going to be the height of the tree, and so it's log n. To traversal, to go through each of the nodes, to visit each of the nodes, we're going to have to go through all nodes, so that one is going to be order n. Well, that's average case. That's a huge improvement from linear search. Let's talk about worst case. Worst case for retrieval is we have a tree like the one we just built, where it's a vine, not a tree. It's still a tree, but it looks like a vine. And so worst case is if we were going to delete TTF, well, the height of the tree is n, and it's not log base 2 of n, but it's n to retrieve it. Well, so to insert, we might follow the same steps as what we did before, and insertion would be order n. And because of that deletion, to find it, it could be order n as well. Now, traversal's no worse. On the worst case scenario, it's also going to be order n. Well, there you go. There's a brief introduction of binary search trees running through some exercises. I hope you enjoyed that.